Bismillahirrahmanirrahim. Assalamualaikum. So we continue our lecture with lecture 4, where in this chapter we are going to discuss on some of the basic computational techniques that are required to solve the governing equations of fluid dynamics. So here in this slide we have the overview of the computational solution procedure. The process of obtaining the computational solutions consists of several stages. Okay, this part we have already covered this in the previous chapters where we talk about the governing equations and all about the conditions. So in order for you to start doing your simulations, you need to understand that first. You need to know which equations suitable for your simulations and what are the boundary conditions that you need to impose on your domain. Okay, this is the first stage that we are going to discuss for these techniques. So the first stage involves the conversions of the partial differential equations, boundary and initial conditions into a system of discrete equations. So this stage is commonly known as the discretization stage. So the process of discretization can be identified through some common methods that are still in use today. So which is shown here, the finite difference and finite volumes. Okay, actually other than finite difference and the finite volumes, it is also worth to mention that there are also other approaches which are finite element and spectral element. I believe like some of you are already familiar with this, like especially for those who are taking finite element analysis or finite element method is use this finite element. Okay, so we are going to talk a little bit on these two approaches. So the finite element method has quite similar techniques or approach as the finite volume, where the main difference between them is the functions used on elements to describe the variations of the unknown variables, where the functions actually is being implemented on for finite element and finite volume actually is different. The finite element method actually has not enjoyed like quite in-depth use in CFD, although there are a lot of commercial codes available that employ this approach. But the problem that finite element method has is it requires quite a large number of computational resources, which makes it costly in terms of computational time, and it also requires like huge processing power compared to this finite volume method. So that's why finite element method not really popular for CFD. Okay, meanwhile, for the spectral elements method, it used quite a similar approach as finite difference and finite element, where all the unknowns of the governing equations are replaced with a truncated series, where we are going to talk about later, which is we are using Taylor expansion series to discretize governing equations. And spectral elements actually compared to finite element, it is a formulation of the finite element method but uses high degrees polynomials as basis functions. So the spectral element here is quite more accurate. It can achieve a very high order of accuracy compared to those of finite element. So the second stage of the solution process involves the implementations of the numerical methods to provide the solutions to the system of to the equations. So a suitable methods for obtaining the numerical solutions for the system will be discussed later on in the later subchapter. Throughout this chapter, we are going to concentrate more on the equations, that typically on solutions that has a steady state flow problem, because these governing equations contains only special derivative, no time derivative, because for our syllabus actually it's quite hard for us to do both special derivative and time derivative at the same time, because it requires a lot of calculation and computations unless we solve it numerically using this CFD software. But if you want to solve it using handwriting, it will be quite difficult and it will consume a lot of time. So most of the problem that we're going to discuss later on in this chapter mainly are steady state flow problems. Okay, so here we are going to talk about the first stage, which is the discretization of governing equations. Okay, as we know that I've already mentioned so many times that before you start your simulations, you need to know which governing equations are suitable for your problems. Usually, governing equations consist of at least you have like continuity equations, you have momentum equations, and sometimes you have energy equations. It depends. If your case involve some temperature, you need to calculate how temperature convected into the fluid. You need to include energy equations, but usually most of the time the most basic equations actually continuity equations and momentum equations, but they one also depends on your problems. Okay, for your continuity equations is quite similar for any kind of problems because it just applies the conservation of mass. Meanwhile, for the momentum equations, it depends. If your problem is laminar, you can just use a normal Navier-Stokes equations. But if your problem is turbulence, you need to use the one that we discussed before. There are some additional equations required to solve turbulence problems where you need to predict the kinetic energy, you need to predict the energy dissipation rate, and also you need to predict from there you can get the turbulence viscosity, etc. So first of all, you need to make sure that you are using the right governing equations. And then it is because for CFD, they have several type of solvers, and this kind of solvers is depends on the situation. It depends on the problems that you want to solve. So if you want to solve laminar problem, you want to solve turbulence problem, they have their own solver where the solver is already discretized all the governing equations to be solved computationally by using this software. So that's why you need to make sure that use the right equations for your problem. All of these discretizations or governing equations already been done in CFD software, so you don't have to do that anymore. Most of the unless you have a new physics you want to apply into your CFD, you want to add some additional terms, so that you need to create or you need to modify the equations by yourself. Okay, but most of the time, if you want to use the existing physics like a classical CFD study like turbulence, laminar flow, you can just use the one that's already incorporated in most of the CFD software. So we'll talk a little bit on the history of this finite difference method. See, it is the oldest methods for numerical solutions of partial differential equations (PDE), and it was developed by Euler in 1768. It's about like 200 plus years ago, and it was used to obtain numerical solutions to differential equations by just using hand calculations. So at each nodal point of the grid is used to describe the fluid flow domain. Okay. Though the Taylor series expansions are used to generate difference approximations to the partial derivatives of the governing equations, and these derivatives replaced by finite difference approximations, which results in equations for the flow solutions at each grid point. Okay, what does it mean by grid point? Actually, you have for example, you have mesh something like this. The grid point is the points. These are nodes, so nodal points. So this finite difference method, it will find all the values at each of these nodes, nodal points or grid points they call it. Like you have like U, V, W, and pressure. They will find it at each of these points. So this method is commonly used on structured grids because it requires high degree of regularity. So structured grids is like this. This is example of structured mesh, and this is example of unstructured mesh. So it will be much easier for finite difference method to be applied if you have a very organized structure, because it finds the value at each of these points. So if you have this and the points is like very randomly located, it will be not really suitable to use this method for this kind of case, unstructured mesh. Okay, the first step towards obtaining a numerical solutions involves the discretizations of the geometric domain. Firstly, a numerical grid must be defined, and in the finite difference method, the grid is usually locally structured. Okay, as we mentioned before, it usually locally structured, and unstructured mesh actually is not really effective to be used for this approach or method. And each grid node may be considered as a local coordinate system. Okay, this is an example of the Cartesian grids for one-dimensional, where you have only one axis in this horizontal, and the bottom one is the two-dimensional Cartesian grids. We have x and y, and each node is identified by a set of I and j. Okay, this for two-dimensional you have I and j. For one-dimensional you have only I. Okay, this is a uniformly distributed Cartesian grid for finite difference method, and if you notice that you have two types of symbols, one is full symbols and the other is open symbols. So the full symbols denote the boundary conditions, the boundary nodes, where first we need to define this. So usually we define boundary conditions either with an exact value or by an analytical equations. So basically you can compute this easily. Meanwhile, for the one that is within this domain is the open symbols, which denote computational nodes, where we need to use the discretized equations to solve this. You compute numerically or computationally. This actually the use of having CFD is to find out to find the value of all of the fields inside. It depends on the boundary conditions. And one thing to take notes is that the lines here, actually they cannot intersect each other. So each of the nodes they can only intersect the nodes. Okay, to illustrate the finite difference method, okay, let us assume that we have a uniform spacing of the grid points in both directions x and y. This is just want to make it easier for us to discuss, and actually it is not necessarily for delta x and delta y need to be equally spaced or uniform. Can easily find cases of problems where it is not uniform. Even when you do your meshing, you can find that the size of the node is not equally spaced. So it's just to make it easier for these derivations becomes easier. We assume that it is equally spaced. So we start with Taylor series, where we have seen Taylor series expansion in solving the conservation equations when we derive the momentum equation before in chapter 3. So here we are interested in replacing the partial derivative with a suitable algebraic difference, which is a finite difference. So for example, in this figure, you can take that in this is ij, this is a generic flow field variable like phi. Okay, phi here, if you remember in fluid mechanics, phi can be any flow field variable. It can be u, it can be v, w, pressure or temperature. It can be any of that flow field variable. So let's say if you want to find u, you can just replace all of the phi with u. Want to find v, you can just replace phi with v. So for example, you have this is Taylor series expansions. So what does it mean is by knowing the value of u, for example, at this point u, so you can find the value of u at the neighboring nodes. For example, if you have the value of u at ij, you can find the value of u at I plus 1 j by knowing the gap and by knowing the del u over del x and del squared u over del x squared and etc. And also you can find the one on the left is I minus 1j. Okay, this is a Taylor expansion, but we don't have all of the informations. Usually we only have the informations until the second order. See, by subtracting these two equations, we obtain the approximation for the first order derivative of phi, which is this. So let's say you want to find the value of this, the value of the derivative of phi at this point. You can use the value at the neighboring to find this value at ij. So you requires to know the value at I plus 1 and I minus 1 for you to find the value at I. Okay, this is the long version, but it can be simplified into this. We just take the first order only. Meanwhile, the rest of the orders, you can truncate it. We truncate it for the first order only. So basically, this is the subtraction, the result of the subtraction of these two equations. Where when you subtract this, it will eliminate all with the same symbols. This will be eliminated. So we have this will plus with this, because plus minus and minus this, and this will be cancelled out. This will be cancelled out, and etc. So you have these terms and you have these terms, but you have multiply by 2. So that's why you can rearrange it to have it this way, where we have the del psi over del x, and the 2 that we got from the subtraction of this, you can move it to down here, and then you can simplify it to this. This represents the truncation error or the finite difference approximation, where we truncate all of the higher terms, higher order terms, and it shows that as we reduce the size of delta x, the space, the spatial distance between the nodes, the lower the error that we will get. So that's what actually we can expect when we have a dense mesh. You can expect actually the error is lower, but the problem is that it need to be compensated with the computing time. Okay, other than the one that we seen before this, by subtracting the two set of Taylor expansion series, where we obtain the central difference, we can also present this the first order derivative by forward difference and backward difference. Okay, the word itself is determined by this, where we have the value of I and j, and then you use the one at the forward, the one step at the front, so where the 1i plus 1. This backward is used due to we want to find this del psi over del x, del phi over del x at phi ij. So we have the value, we have the information of the one which is behind it, so it's backward difference. So we want to find the difference over x. So if you look at the truncation error, they have a slightly different, okay, the representations of truncation errors. If you can see that for forward and backward, they are quite similar. And for central difference is different. So actually the delta x usually is very small. Okay, if you have a very small number, like for example 0.1, if you times by itself, it become smaller than the original value. Like if your delta x equals to 0.1, if you make it power of 2, it becomes 0.01. So that means that the truncation error for central difference is lower or smaller compared to those of forward difference and backward difference. Said that the smaller the delta x, the better the agreement with the actual value. So you can see here, this figure down here represents the first order derivative for del phi over del x. Okay, you have a value of phi and versus the value of x. So we have this is your I, and this is when you use backward difference, so we refer to this and this. So if we use forward, we refer to I and I plus 1. So if you forward, basically you get this kind of value, and actually the one that we want to find is the derivative del phi over del x. So we know that the value at I here is this, and this is the phi, and the phi at I plus 1 is this at c. So if you find the derivative, we find the gradient, actually this is what we will get. The slope is this, b and c. And if we do the backward difference, this is the phi I minus 1 and this I minus 1, which is a. So the gradient is this, but actually the exact gradient is this. And if we use the central difference, we use the value of c and a instead of using b and a, b and c. So we want to find the derivative or the gradient at point I. We use the value at c and a. So the difference between these and divide by 2 times delta x. So that's why we use the uniform or the same gap for delta x, so that we can use the multiplication to delta x. If it is not similar, we cannot use to delta s. Instead, we need to use the delta of this plus delta of this. So if you can see that the gradient between A and C is very close to the exact gradient at B. So it shows that the central difference has a better agreement with the actual or exact value. Other than the first order derivative, see the second order derivative also can be obtained by using the Taylor series. Okay, if you remember the first order, actually in Navier-Stokes equations, you require first order to solve the additive terms. And if you look at the diffusion part, where we see the effect of the viscosity, you can see the second order terms in that equation. So we require to discretize it to obtain the second order derivative as well. So if you remember before this, for the first order derivative, we subtract the Taylor series from these two different nodes. But as for the second order derivative, we acquire it by adding the Taylor series. So if we look back at page 5, okay, here we have these two equations. So instead of subtracting these two, we add these two. So by adding these two, basically we are going to eliminate the first order terms. Meanwhile, the second order will be added between the one after and the one before, the one on the right and the one on the left. And meanwhile, the third order will be cancelled out because we adding them. Okay, and then use the same methods, and then we can just take the higher orders as the truncation errors. So we can see, because these are the results of the additions of those two terms. Okay, and whatever at the higher order, we can just take it as a truncation errors. Okay, the one at the top is for the one in x directions, and the other one is in y directions, y components. This represents the central finite difference for second order. And a Taylor series expansion for time derivative can also be obtained using similar method as for space. Okay, the one that we discussed just now, the first order and the second order, is in space, which is as a functions or the partial difference with respect to space x and y. We can use also the same method as by using the Taylor series expansions to find the time derivative. If we talk about steady state flow, basically we can just ignore this term. So that's why in this syllabus, usually we will focus more on steady state, because it will actually quite troublesome for us to solve spatial, and then we need to do time step as well. Okay, every time we do spatial, and then once it's already converged, then we need to do time step, which requires a lot of work. So for us to do it using like hand calculations, usually we just focus on steady state instead of focus on the transient, which is time dependent. Okay, before this we talk about finite difference method. Now we go into finite volume method. Actually, relatively compared to finite difference method, finite volume method actually is quite recently introduced, which is around 1970s, which we can say that it's about like 200 years after finite differential method was introduced first by Euler. The computational domain for FVM, we call it FVM, is subdivided into a finite number of control volumes. It is expressed as the exact conservation of relevant properties for each of the control volumes, where this is what we discussed before, where the conservations of volumetric flow rates, like we have a volume, all points or the elements in your mesh, not necessarily in structured but also in unstructured mesh, where we treat each of these volumes as your control volumes, which is within or confined by the grid lines. We treat it as a control volumes. So all of the properties in this control volumes is treated as need to be conserved. And at the center of each of the control volumes is where the variable values are calculated. And interpolation is used to find the variable values of the contour volume surface. So at any of the points, we use interpolations to find or to estimate the variable values. And since it works with contour volumes and not grid intersections like those of finite difference method, so it has the capacity to solve any type of grids. Because like if you remember the FDM or finite difference method, it is not suitable to be used for unstructured mesh. Okay, meanwhile, compared to structured mesh, actually unstructured mesh is more suitable to cater or to solve problem with a very complicated shapes. Like if you have a very acute angle where you cannot fit in your like four-sided structured nodal or mesh into it, so it will be much easier if you have a triangular mesh instead. As you can see here, you have this N, which is N here is representing the directions. Still, if you remember in fluid mechanics, we talk about these contour volumes like the mass in and mass out, the properties that goes in and goes out. So it is indicated by N, where N represents, okay, if the flow or the properties moving out from the contour volumes, we take it as positive. If the properties is going into the contour volumes, pass through the surface, which is perpendicular, which is 90 degrees or normal, it will treat it as negative. Okay, if it is outward, it's positive. If it goes inward, it's negative. That is what represented by N. Okay, this is the equations for finite volume method. By applying Gauss divergence theorem, this thing is quite mathematical. So by using this Gauss divergence theorems to the volume integral, so the first order derivative of phi into dimensions can be approximated. Okay, the first one on the top, this is the derivative of phi with respect to x in x directions, and the bottom one is in y directions, where v here represents the volume. Okay, this is the change in volumes, and this is phi over del x with respect to the volume, where if we divide the volume with x, we will get the area, the change in the area, and we have phi here, and it approximately equal to the summations of the product of that properties, the flow variables that you want to find, it's either u, vw, or pressure or whatever, multiply with areas. And n here represents the number of, n here is denotes the number of bonding surface. Okay, like if you have example the mesh before, we have a 4 side, so n equals to 4. If it's a triangular, n equals to 3. So this is depends on the type of elements that we are using. Okay, we take this one example of how to discretize equations. Okay, here this example is where we are going to discretize or find the discretized form of the two-dimensional continuity equations by using the finite volume method. Okay, finite volume method is the one that we just discussed just now. By using a structured uniform grid arrangement, as we know that continuity equations for two-dimensional is defined as this: the del u over del x plus del v over del y equals to zeros. Okay, here we apply the finite volume method discretize equations to solve both in x and y directions. So if you remember, we have a del phi before, but here we want to solve the flow field of u, velocity in x directions. So this is the approximations where you can use. So we have a 4 side here, hence here we have n equals to 4. So each of these faces is represented by east to the right and north to the upward, and to the left is west, and downward we indicate it as south. East, north, west, and south. So for x directions, we just take the one that in x directions, which is east and west. So whatever the variations, there is no u towards a direction, and there is no u velocity towards s directions. There is no u in y components. So we take this as, okay, once, as we know that actually it needs to be, once need to get in and one need to get out from the control volumes to make sure that the continuity is there to fulfill the continuity equations. So one will be negative, one will be positive. Okay, negative means that it is going in, and positive that means that it is going out. So we take that is going out to the right and is coming in from the west. So that's why we have positive and negative here. Meanwhile, for the north and south, take it as zeros. Okay, meanwhile, in y directions, it's quite similar. We take v in y directions, use the same equations, and n equals to 4. As for this case, the component to the east and west, we take it as zeros. There's no v in towards E and W directions, which is in X directions, and we take that it's coming in from south and going out towards north. So you have plus and negative there. Okay, that is if we have four sides. Like four sides, we have a 4 summation of 4. So we supposed to have a 4 terms like this. But if, like for example, we have like 3 sides, so we can expect that we only have 3 sides. And for 3 sides, of course, it's not going to be something structured like this. This is facing like exactly parallel with the x directions, and this is parallel to y directions. Of course, you're going to have some angle. So that is where n plays its roles. Where if you refer back in fluid mechanics, where n equals to cos theta, the angle. So here is we have this normal angle. So that's why this is can be just terminated, because it will give you the cos of the theta will give you 0. So it will cancel out. It will be terminated. So the cos of the theta will give you 1 and minus 1. If you remember, if we refresh, go back to that topic in fluid mechanics. The same goes to this. So if you have triangles, you will expect to have that kind of term. You have cos theta, so it will be a little bit different, and the total of terms is only 3, or not 4. Okay, and then we need to determine the phase velocities from the values located at the centroids of the control volumes. If you look back from this figure, this is a lowercase e, n, w, and s, and we have a uppercase e, n, w, and s, which represents the centroid of the neighboring elements. And here we have a p for these control volumes that we are focusing on, and the one on the right is e, and at the top w is on the left, s at the bottom. So they are all indicated by this. And the relationship between the velocity at the surface of the control volumes that we are looking at is equals to the velocity of that centroid of the control volumes that we are focusing on, plus the velocity of the center of the elements that this UE is pointing at. Actually, these are derived from Taylor expansion series as well. So the final form of the discretized continuity equations becomes this. So we just substitute these equations, this term, into the one that we found here. Okay, this is the one in x directions, and this is the one in y directions. So we put it all together. See this, and we assume this is 2-dimensional problems. So usually for 2-dimensional problems, for the width in z directions, we can just treat it as unities to make the equation simple. Basically, the area of the east and west, which is the area here, is supposed to be the length of this multiplied with the width, which is into the pitch in z directions. So to make it simpler, we just treat z, the width in z directions, as 1. A is equals to delta y times 1, and this is for those at the one at the top and bottom. So the area here is delta x times 1. So that's why we have the area in that direction, and the facing north, and the area facing south is equals to delta x times 1, which is times z. And then we can just substitute these equations into here. So as we substitute with delta y, This is up to you data as well, and etc. So when we get against it, basically we can eliminate this UP, and at the end, this is what we get. This is the final form of the discretized continuity equations for two-dimensional problems. So this is the original continuity equations, and this is the discretized continuity equations.